I was watching a video the other day, just doom scrolling, as you do, and I stopped on this clip of someone walking for the first time after a double knee replacement.
Oh, yeah.
And it's emotional, right? I mean, there are tears, the family's cheering, the grandkids are clapping. It's a genuine capital M medical miracle.
Oh, absolutely. It's restoring life. You're giving someone back their mobility, their independence. It is emotional.
But, because I'm me, and because I've been buried in this sack of research we're looking at today, I couldn't stop staring at the actual knees.
At the hardware.
Exactly. I wasn't seeing the miracle, I was seeing the engineering. I was thinking about the fact that inside that person's leg, there are pieces of metal and plastic that have to slide against each other under full body weight millions of times without failing.
And without generating debris. That is really the key.
Exactly. We gloss over the how. We see the surgeon as the hero. But today, I want to look at the hidden hero, the manufacturing. Specifically, the extreme precision machining required to build these things. We're doing a deep dive into the technical solutions provided by a company called ISCAR.
Which is fascinating because ISCAR is basically holding a masterclass here on how to cut the uncuttable.
That is the mission for this deep dive. We're going to unpack how you take some of the hardest materials on Earth and, some of the softest actor and shape them into a knee implant that is so precise it essentially renders the human touch obsolete.
That's a bold way to put it, but you're not wrong. This is about removing variables. It's about industrial certainty in a biological environment.
So before we get into the, the drill bits and the microscopic tolerances, help us visualize the anatomy here.
Yeah.
Because a knee implant isn't just a hinge, is it? It's not like a door.
No. A door hinge is a single axis. Your knee is it's a complex joint. It rolls, it slides, it rotates, it takes impact.
Right.
So to mimic that, an artificial knee is really a system of 3, sometimes 4 interacting components. Think of it as a high-stakes sandwich.
Okay, I like that. Let's build the sandwich. What's the top slice?
On top, attached to the femur, your thigh bone, you have the femoral component. This is the part that usually looks like a highly polished metal claw. It mimics the round ends, the condyles of your thigh bone.
So that's your main bearing surface.
That's it.
The shiny, curved metal part.
Okay, what's on the bottom?
Attached to the shin bone is the tibial tray.
The tray.
It's the structural base plate. It's usually a flat metal plate with a stem or a keel that goes down into the bone to anchor it. It's the foundation of the house.
And in the middle, because you can't just have metal grinding on metal.
No, that would be catastrophic. You'd get metal ions released into the body, you'd get debris. It would fail very, very quickly. So sandwiched in between is an insert made of UHMWPE.
Ultra high molecular weight polyethylene.
Exactly. It's a specialized medical grade plastic that acts as the cartilage replacement. It clips into that bottom metal tray and the top metal claw slides around on it. So the manufacturing challenge is actually a triple threat. You have to machine these incredible organic curves for the top part, perfectly flat surfaces for the bottom part, and then switch gears entirely to machine soft plastic for the middle.
And you have to do it with zero margin for error. We are talking about validated medical processes.
Right.
If a tool leaves a microscopic burr, or if the surface finishes off by a micron, that implant fails prematurely. The patient is back in surgery, which is the absolute worst case scenario.
The stakes are incredibly high. So let's start with the hard stuff. The femoral component, the claw. Looking at the ISCAR technical overview here, the diagrams of this part, they look like a nightmare to program. There isn't a straight line on it.
It's all free-form 3D surfaces. It has to be organic to match the patient's anatomy and movement. You can't just cut a square block. But the geometry isn't even the biggest headache here. It's the material. The source highlights cobalt chromium alloys.
I know cobalt chrome from aerospace.
Yeah.
It's used in jet engine turbines, right?
Yeah.
Because it can take heat.
It is, exactly. It's chosen for medical implants because it is incredibly hard, wear-resistant, and biocompatible. It doesn't corrode inside the fluids of the human body.
Okay.
But those same traits that make it great for a patient make it a machinist's worst enemy.
Why? What happens when you try to cut it?
It's abrasive, so it just eats tool edges for breakfast. But the real killer is something called work hardening.
I've heard this term thrown around. Let's unpack that.
Yeah.
What is physically happening to the metal?
Okay, so imagine you're rubbing your skin. If you rub it gently over time, you get a callus, right? The skin gets harder to protect itself from the friction.
Sure.
Cobalt chrome does that, but almost instantly. If your cutting tool isn't sharp enough, or if it sort of rubs instead of slicing, the metal literally hardens at the point of contact.
So as you're trying to cut it, the material is actively changing its properties to stop you from cutting it.
It's fighting back, exactly. You generate massive heat, the tool dulls, the material hardens even more, and suddenly your expensive drill bit just snaps or burns out.
Lovely. So how does ISCAR navigate a material that fights back?
It's a multi-stage attack. First, you have roughing and semi-finishing. You need to remove the bulk of that hard metal quickly to get close to the final shape.
Right.
For this, ISCAR points to their solid mill premium line. These are solid, carbide, ball nose end mills.
Balls make sense for the curves, but is there anything special about the cutter itself, or is it just a really hard piece of metal?
Oh, it's all about the geometry. The source notes these tools have an unequal angular tooth pitch.
Okay, hold on. Unequal angular tooth pitch. That just sounds like pure tech jargon.
It does.
I mean, intuitively, wouldn't you want the teeth to be perfectly symmetrical?
Yeah.
Perfectly balanced?
Intuitively, yes. You'd think symmetry is balance. But think about soldiers marching on a bridge. If they march in perfect unison, left, right, they create a rhythmic frequency.
Resonance, which can actually damage the bridge.
Right. In machining, perfectly spaced teeth hitting the metal create a harmonic frequency. We call it chatter. The tool starts vibrating. And vibration leaves ugly marks on the surface and breaks tools.
So by spacing the teeth unevenly,
you break the rhythm, you disrupt the harmonic frequency before it can build up. It's like noise-canceling headphones, but for physical vibration.
That's brilliant.
It stabilizes the cut, which lets you run the machine faster, even in this work-hardening nightmare metal.
That is a brilliant bit of physics. Okay, so that gets the shape rough cut. But this femoral part needs to be mirror smooth. If it's rough, it's going to act like sandpaper on that plastic insert.
Correct. And this is where ISCAR suggests a tactic that I found really interesting. For the finishing pass, they switched to an 8-flute cutter.
8 flutes? That seems like a lot.
Yeah.
Usually in a wood shop or a basic garage, you see 2, maybe 4 cutting edges.
It is a lot, and there's a trade-off. More flutes mean less space between them for the chips, the waste metal to escape.
Right.
But if you're just taking a tiny final skim coat off the surface, you don't have big chips.
So you can crowd the tool with cutting edges.
You pack them in. More flutes mean more points of contact per revolution. It increases the overlap of the cuts. ISCAR calls this superior surface flow.
Which translates to what for the manufacturer?
It translates to a surface that looks like it's already been polished, and that is the holy grail here. The source explicitly mentions this minimizes corrective polishing time.
I want to put a pin in that because the idea of minimizing polishing seems to be a recurring theme in this document. We'll come back to why that's so critical later on.
It's the central thesis of their approach, really.
Okay, so we've survived the cobalt chrome femur. Now we move down to the shin bone, the tibial tray. This looks deceptively simple.
It does.
It's just a tray. It's flat.
It looks like a simple plate, but the engineering requirements are totally different. The femur was about curves. The tibia is all about flatness.
Why is flatness so hard? Can't you just mill it flat?
You'd think so. But remember, we're often dealing with titanium alloys here for the tray. Titanium is lighter than cobalt chrome, which is good, but it has very low thermal conductivity.
Meaning it doesn't dissipate heat well.
It acts like a heat insulator. When you cut steel, the heat mostly leaves with the chips flying off. With titanium, the heat stays right there in the tool and the part. And if that titanium tray gets too hot during machining, it warps, it bows.
And I'm guessing if the tray is warped, the plastic insert won't click in properly.
Precisely. It will rock. And if it rocks inside the patient, the joint becomes unstable. So you have to machine it flat and keep it flat while battling massive heat buildup.
So what's the weapon of choice here?
ISCAR recommends a tool called the Dove IQ Mill 845.
The Dove IQ Mill. Sounds peaceful.
The name might sound peaceful, but the engineering is aggressive. It's a face milling cutter that uses double-sided square inserts. But the magic is in the angle. It produces what the source calls a soft cut.
A soft cut on titanium. That sounds contradictory.
It does, doesn't it? It refers to high positive inclination. So think about cutting a block of hard cheddar cheese. If you push the knife straight down brute force, you have to push really hard, and you might crush the cheese.
Right, you crumble it.
That's a hard cut. But if you slice the knife across at a sharp angle, it glides through with very little pressure. That's a soft cut. The Dove IQ mill slices the metal rather than plowing through it.
And less pressure means less friction? which means less heat.
And less heat means the part stays flat. Bingo. It allows them to do roughing and finishing with the same tool, holding tolerance the whole time.
There's another system mentioned for the tibial tray that seemed focused on the economics of the factory floor. The multi-master.
Oh, the multi-master is fascinating from a logistics standpoint. It's a modular system.
Yeah.
You have a shank, the long steel holder, and then you have these little solid carbide heads that screw onto it.
Like changing the bit on a multi-screwdriver.
Similar concept, yeah. But with micron-level precision, the source emphasizes that this reduces inventory. Think about it. Instead of stocking 500 expensive, solid carbide tools that are a foot long, you stock 500 tiny heads and just a few handles.
That's a huge cost difference.
Massive! And for medical manufacturers who are under huge pressure to cut costs, that's vital. Plus, you can swap the head without taking the tool out of the machine. You switch from a slotting head to a profiling head in seconds.
It seems like ISCAR is trying to solve the downtime problem just as much as the cutting problem.
In high-volume manufacturing, downtime is the enemy. If the machine isn't cutting, it isn't making money.
Okay, so we've built the metal foundation, we've done the femur and the tibia, now we have to machine the cushion, the cartilage, the UHMWPE.
The plastic paradox.
I love that term. You'd think, okay, the hard part is over, I'm cutting plastic now, easy mode.
And that is exactly where machinists get into trouble. The source makes it clear. UHMWPE introduces a completely different set of considerations.
This is simply because it's soft?
It's because it's ductile and elastic.
Meaning it's stretchy?
It's stretchy. It's like trying to machine a gummy bear. If you push a dull tool against it, the material doesn't cut. It squishes away. It deforms.
And then what happens when the tool passes?
It springs back. You think you've cut a 10-millimeter hole. You measure it later, and it's 9.8 millimeters because the plastic sprang back after the drill left.
So you have immediate size deviation.
Instantly.
So you can't use the same tools you used for the titanium.
Absolutely not. If you use that negative rake plowing tool on plastic, you just generate heat. And what does heat do to plastic?
Melts it, smears it.
Exactly. And smearing is catastrophic. You also get what the source describes as continuous ribbon-like chips.
Meaning the waste material doesn't break off into little flakes.
No, it comes off as a long, continuous string. Imagine a localized tornado of plastic spaghetti wrapping around your spinning tool.
That sounds like a mess.
It can clog the machine, damage the surface finish, or even snap the tool.
So how do you cut the gummy bear without squishing it or melting it?
Sharpness is king. You need a tool so sharp it shears the material before the material even realizes it's being touched. ISCAR uses their helipless cutters here. They have super positive chip formers.
Again, positive meaning that slicing angle?
Yes. Extremely aggressive, sharp angles. It cuts without local pressure deformation. It just snips the plastic cleanly.
And I noticed a detail here that brings us full circle on the flutes. For the metal femur, we used an 8-flute cutter. For the plastic pockets, they recommend a 2-flute cutter. Why the big drop?
It's purely about that spaghetti we talked about. If you have 8 flutes, everything is packed tight. There's no room for a long plastic chip to escape. It would clog instantly.
So you use 2 flutes to create big open valleys for the waste to fly out.
Exactly. Chip evacuation becomes the priority. And they polish the flute so the sticky plastic slides right off.
It's impressive how the machinist has to completely invert their brain. From tough and heat-resistant for metal to sharp and spacious for plastic.
Yeah, it's mental gymnastics. But here is the why behind all this effort. The source explicitly says the goal is achieving surface finish from machining alone.
We're back to the polishing thing. Why is ISCAR so obsessed with avoiding manual polishing? I mean, we usually think of hand-finished as a sign of quality.
Handcrafted.
In a luxury watch, sure. In a leather bag,
Yes.
in a medical implant. Handcrafted is a nice way of saying inconsistent.
Because humans have bad days.
Humans vary. If you have a technician named Steve polishing the plastic inserts, maybe on Monday he polishes a little harder than on Friday. Maybe he removes 10 microns too much material on the left side. Now that geometry, that complex rolling and sliding curve we designed, is altered.
And the patient ends up with a knee that clicks or wears out unevenly.
Exactly. The human touch introduces error. By using these ultra-precise ISCAR tools to get the finish perfect right off the CNC machine, you guarantee that every single knee is identical to the CAD model.
We're designing the human out of the loop for the sake of the human who will wear the knee. That's the paradox. To save the human, you have to remove the human from the manufacturing.
Now, zooming out a bit, we've talked about the tools, But the source document spends a decent amount of time on the process. ISCAR isn't just shipping these tools via Amazon and saying good luck.
No, and in the medical field, they can't. The industry is heavily regulated. You have FDA requirements, ISO standards, you need traceability, you need to know exactly how long a tool lasts so you can change it before it breaks or gets dull.
Predictability seems to be the product here, not just carbide.
Spot on. The source mentions that ISCAR engineers actually get involved in parameter definition and tool path optimization. They are on the factory floor helping write the recipe.
Why does that matter so much to the manufacturer?
Time to market. In pharma and medtech, there's something called process qualification time. It can take months to prove to regulators that your manufacturing process is safe and consistent.
And if you're guessing at your tool speeds, that takes longer.
Right. If ISCAR comes in and says, we have validated data for this cutter in cobalt chrome, run it at these speeds with this coolant, you slash that qualification time. You get the implant into production and into patients months sooner.
It's really a convergence of material science, geometry, and legal and regulatory strategy.
It is. It's industrial certainty. When you're drilling into materials that cost a fortune to make parts that go inside a body, you don't want surprises. You want boring, predictable perfection.
I think that's the big takeaway for me. We look at a knee replacement and think about biology, but really it's a triumph of metallurgy and machining.
It's where the industrial meets the biological. And as implant designs get more complex, we're seeing patient-specific implants now, custom-shaped to your specific anatomy. The machining has to get even better. You can't design a better knee if you can't build it.
The design is only as good as the cutter. I want to leave the listener with a thought that you sparked earlier. We touched on the idea that hand-finished is actually a negative term in this industry. It makes me wonder, as we move forward into this world of AI and hyper-precision robotics, are we going to see that shift in other areas?
How do you mean?
Well, we cling to this idea that the human touch adds value. But in a world where performance and safety are paramount, the human element is increasingly the liability. The goal of this high-end engineering is to create a system so perfect that it doesn't need us to smooth out the rough edges.
That is a provocative thought. We are engineering ourselves into obsolescence, one perfect micron at a time.
Something to chew on, and definitely something to think about if you or a relative is getting a new knee soon. There is some serious sci-fi level engineering happening under that scar.
Indeed there is.
That's it for this deep dive into ISCAR's tooling solutions. Thanks for geeking out on drill bits and bone implants with us.
It was a pleasure.
See you next time.